Cool. Well, thanks everyone. It's really great to be here. This is my first time at NITMB, and it's great to see a lot of familiar faces. So yeah, this is a fairly new direction for me, and I'll talk about the also a very different connection to extremes, more kind of along the lines of extremal statistics. And to start, my goal for the talk is just to kind of convey this. As I said, it's a new area. Just convey. I think it's super cool. And also introduce you to some ideas that were not, at least for me, part of my, let's say, like my education in sort of mathematical biology. So, and I think are relevant to a lot of people here, perhaps. So, there we go. Okay, so just to set it up, so I think most of us are familiar with the idea of supervised learning. We're given objects and labels for those objects, and the goal is to predict the label of a new object. So for example, this is a classification problem where I have a bunch of objects. They have features, which are the shape and the color, and then they have labels, which are black or white. So it's a classification problem, and then we would want to predict the label of a new object. In this case, it's kind of silly because it's in the training set, but we would predict that would be white. And a multiple instance learning problem is another type of supervised learning problem where the objects that we're given are sets, okay, sets of other objects. And we call the objects inside the boxes instances, and we call the boxes bags. And the goal now, just as before, is to predict the label of the new bag. And in some sense, it's just another supervised learning problem with a more complicated object that we're putting in, an object that is a set. So remember, the order doesn't matter. But what I'm going to try to convince you is that the idea of having set-valued inputs, and along with the fact that usually the way the labels are constructed in applications is based on some extremal selection rule, leads to some kind of interesting questions in probability, especially high-dimensional probability and extremal statistics here. So in this case, would anyone guess what the label would be? And there's multiple answers. White. Actually, there's multiple ways you could have labeled this based on the training data, but one of them is black. You could notice that there's the triangles are in the black ones. But again, we have to make an assumption about how what the mapping is in this case. Okay. So where does this come from? This is supposed to be kind of a math biology conference, and I'm just talking about shapes and colors in bags. So the early work on this, really the paper that everyone cites that kind of brought this problem to people's attention was a paper by Diederik et al. In 1997. And they were interested in, can you predict whether a chemical is a musk? So if you don't know a musk, they're certain odorous chemicals that are naturally occurring. And I guess that they're used in perfume. I actually haven't given this talk a couple of times, and I still haven't gotten my hands on some musk. I'd like to see what it's like. But they're naturally occurring, so the musk deer is one source of these chemicals. They have a gland that emits these chemicals. And so people want to find synthetic chemicals that have the same properties as these musks. And so it's a supervised learning problem where you're given a bunch of examples of chemicals, and some experts have labeled them as, is it a musk or not? And there's classification version, and then there's more of a regression version where it's a real valued label version where it's like, how much of a musk is it? And there's data sets are out there. And so that's the problem, standard supervised learning problem, chemicals, is it a musk? And I should say also that they were actually, this group that studied this, they're actually trying to do drug discovery and went to this musk problem as sort of an easier example, something that where the data sets were a little more controlled. And their thinking at the time was that, well, this is really whether something is going to be a good musk or not is about the 3D geometry of the chemical in space and whether it is binding to some receptor, okay? But the molecules can have many conformations in equilibrium. They can have multiple conformations. And so really what we want to do is we want to think about, as the input to our learning algorithm, actually taking all those conformations and making a bag out of those conformations where the instances are some sort of vector representation of that 3D geometry of the chemical. And we don't know which conformation is the one that's actually doing the action. It's assumed that there's maybe one there that's really causing it to have that odor. We just see whether the whole bag as a whole is a musk or how much of a musk it is. So that was how they thought about this problem, and that gave rise to this multiple instance learning framework. And it's since kind of become quite pervasive of an idea in machine learning. So there's certain problems that are just obviously or naturally multiple instance learning problems. One of those is immune repertoire prediction. So you have here the bags are people, or rather someone's immune antibody sequences. And then the labels are, is that person have immunity? You want to predict whether a new person has an immunity based on their sequences. This is one where the number of instances in a bag is massive, like tens of thousands. And there's other problems where you can essentially turn a problem into, that's maybe not obviously a multiple instance learning problem, into one. And an example would be pathology slides. So if you have an image and you're trying to identify whether there's some cancer in that image, well, the cancer is very localized. And so what you would do is you chop the image up into little pieces, and this is much easier to train in a machine learning framework if you've sort of recast it as a multiple instance learning problem, where the bags are the sort of image chopped up into the little you might call them voxels of that 3D image. And then there's other problems but they're not in biology, so I won't talk about it. But text document classification and object detection are very similar things you can turn into multiple instance learning problems. Sorry. So I'm going to talk a little bit about, I'm going to give you some background on sort of the early thinking about this problem and the types of models that people consider and how they approached it. And I'm also going to, on this slide, introduce sort of the notation that I'll use throughout the talk. So I'm going to use XK to represent a bag as a matrix. So I have M bags. That's think of that as my training data. And the rows of the matrix are the instances, or the embeddings of the instances. And then those are vectors in 3 dimensions, and each dimension is kind of a feature of that. So you could imagine it's like, the shape, color in the example before. And then there's the labels are going to be the Ys. And another important piece of notation or definition is the idea of an assignment. So an assignment is just a function that takes us from the bags, and for each bag, it assigns us an instance. Okay. Now, the early models, like the ones that people were using for this musk data set, not so much the pathology slides and these other things, but for those early models of drug discovery in musk, the thinking was that there's a single point in feature space, which they call a concept point. And the way that the labels are constructed for the bags is by finding the instance which is closest to that concept point, and then labeling the bag as some function of that distance. And you can, I won't get into this, but there's kind of biophysical motivation for the G function that you would pick here, or physical motivation for the G function there. So we're selecting the instance closest to that concept point. We're using it to construct the label. And then this also induces an assignment, because now if you look at the index of the instance, which is closest to the concept point, that gives you this assignment of bags to instances. Okay. And there were roughly, in the early work, there were kind of I've listed 4 different sort of ways of thinking about it. So they had a sort of geometric approaches, which really only work for the classification version of this problem, where you're essentially constructing rectangles that contain the positive but not the negative bags. So it's like kind of like a discrete geometric framework. There was this diverse density approach, which is like kind of MLE, maximum likelihood estimate, and doing gradient descent. There was support vector machines. But what I'm going to talk about is this EM, which outperformed these other methods on the early models. So I'm going to tell you a bit about this EM algorithm and how it applies. And this is just, this is more general than multiple instance learning, and this is I think a rather good thing to know in general. So what is the EM? So you have a problem, you're trying to do maximum likelihood estimate. So you have a likelihood function, you have a loss function, which is a log likelihood of some probability of seeing the data conditioned on the parameters. And I'm just going to use P, whether it's probability measure or density or whatever. There's so much. And the assumption is that there's some latent variable, okay, where to obtain this likelihood, we've marginalized over that latent variable, which we don't see. And if we had known that, if we also had that access to that latent variable in our data, that latent variable being an MIL, the assignment, the problem would be easy. It would be much easier to perform the optimization here. Easy means convex in optimization often, okay? Or it might have vanishing, maybe the full thing has vanishing gradients, but if we know the assignment, it doesn't. And the EM algorithm, this EM algorithm is essentially based on a trick. And the trick is we're going to take that log likelihood and we're going to represent it as an expectation over the posterior distribution of the latent variable at a different parameter. So we have a guess of the parameter. We can rewrite, this is just some kind of hooting and hollering with Bayes' formula and rearranging things, right? And what we get is this likelihood split up into two terms, this log likelihood split up into two terms, where one of them involves the expectation of the log of the joint density of the data in the latent variable, and the other is the predictive distribution of the latent variable. Okay, whatever the dependence is on theta naught in these two terms, it must cancel because we're just rewriting the log likelihood. But the cool thing is that if we look at the difference between this log likelihood at the guess and another parameter value, the H term turns out to be the KL divergence between the predictive distribution of the latent variable at the two parameter values. And therefore, if we just look at the Q term, if we just optimize the Q term, the loss function is going to go up. Okay, so this is the idea of the EM algorithm, which is simply just iteratively doing the optimization of that Q function. And it essentially has turned something that some optimization problem, which might be non-convex, to something that in approximating it with an iterative sequence of convex optimization problems. I just find this to be a very cute idea. And it honestly wasn't something I learned about until I did this project. So yeah, appreciate it. So in MIL, the thing in the multiple instance learning problems, especially in these early models, is that we're in a limit. We're in a limit where the prior distribution of the latent variable, given the predictors, meaning before we've seen the labels, we have, if we see the instances, we have essentially perfect knowledge of what the assignment should be. So it's really kind of a limit of this EM algorithm, and where this becomes a delta function. And so that is kind of the basis of the early approaches to solving this multiple instance learning problem with the EM algorithm, where you find the assignment, which is extremal, and then you'd use that extremal assignment, plug that into the log likelihood, and then optimize the likelihood and just go back and forth doing that optimization. The hope is that it would converge. There's no proof of when this converges, or it's just something they tried it and it works. And I'm going to talk a little bit about sort of the role of sort of some probability theory questions you can take away from this, but I just want to point out, and I'm going to circle back to this later, this actually isn't the right limit of the EM algorithm if we start with a noisy model where the labels and the selection rule are noisy and take the limit. And that has to do with the fact that really we should be using, if we're saying that the labeling is noiseless and the selection is noiseless, we should be actually using the labels to compute the assignment. So I'll come back to that. But let's just take this. It works. They tried it. It works. And consider a simple example, okay? So let's say that D is 1 minus V dot X. Okay, this is not the Euclidean distance, but if the things are on the sphere, it's the same thing. So this makes things a little simpler. And also this was what you get if you're sort of in high dimensions. So a very simple version of this model would just be, I'm going to dot product the concept point with all the instances and then take the extremal dot product, okay? And in this case, the MLE that you get at each step of the EM algorithm is just obtained by a linear regression problem, like standard least squares estimator, where the design matrix now has rows, which are the instances that you have selected from your assignment. Is that okay? Just a standard linear regression problem. And the kind of question we can ask about this is mathematicians are like, okay, how is this if we just have random instances, right? Lots of people have studied Musk data sets and other sort of data sets out there. I just want to know, if we just have random instances, okay, what can we say about this, the solution to this regression problem in the limit, in some limit, as n is large, as m is large. And I'm going to use, by the way, v star and psi star for the true assignment and the true concept point. So of course, this is going to depend on what that assignment is, right? If some of the instances are matched and some of them are not. So if some of the components of psi are psi star, match with psi star, and some of them don't, then we have a design matrix where some of the predictors were actually used to produce the labels, but other ones were not, okay? And we can actually, this is kind of a warm-up problem you can do, is to say, okay, well, what if I sample the assignment uniformly, okay, from the space of all assignments, but condition on a certain fraction of the assignments matching, right? So some of them are matching, like I was saying, some fraction f of them match, and then some of them are mismatch assignments. Then, if I take m to infinity, the solution to this regression problem actually converges to a scalar multiple of the true concept point. And the scaling factor, this phi, essentially, it involves f, it involves n. I'm going to show later in the more general result what the numerics look like. But it involves these scales s in v, which scale is the log of n. Remember, n is the number of instances in each bag, and negative 2 ln of n. Okay, and this is going to be, this is a number that's less than 1. It's going to go to 0 when n, when f is 1 over n, and it's going to go to 1 when f goes to 1. Okay, so that tells us that basically if we solve this regression problem, we get a scalar multiple of the right thing. And I'm going to talk about the implications of that for actually the algorithm in a minute. But where do these S come from in the V? They basically come from extremal statistics. And that's not at all surprising because we're dealing with, again, a design matrix where some of the rows are selected based on an extremal principle. So of course, we're going to get the extremal statistics. In particular, we get the second moment of the extremal of NIID Gaussians appearing in this formula. And you can, if you're playing like extremal statistics bingo, you can now check off this thing right here, this result right here, classic result in extremal statistics. And so, okay, where does this, just to get a little more sense of like the proof of this kind of thing. So I would just take my least squares estimator, which involves these covariance matrices of the instances which are selected by this assignment, and then a cross covariance matrix between the assignment and the true assignment. And basically, if you were just the easy case, and you without loss of generality, you can take just v, the concept point, to be identity vector, and then you get that the averages of these covariance matrices are rank 1 perturbations of the true covariance matrix of the instances that we've sampled them from. And then the result basically follows from applying the Sherman-Morrison formula and then some concentration results for empirical covariance matrices, with the subtlety that once you've conditioned on 1 minus f, those results don't apply directly because the rows are not independent, but it's easy to deal with that. Okay, so that's kind of the idea, showing that just in this, I'm just trying to set up that in a simple case, we get sort of questions about extremal statistics and estimating covariance matrices with extremal rows in them. Okay. Now the implications of this are that for the algorithm is that if we're actually able to get that concept point, get a scalar multiple of that concept point, right? If we put that back into the argmax to try now to get the assignment that goes with that, right? In the algorithm, we're alternating between estimate the concept point, estimate the assignment. Well, it doesn't matter that we don't have the correct concept point. We only have a scalar multiple because we're going to get the same thing from the argmax anyway. And now the question is, how large does M need to be to get a good approximation of the direction from just a completely random assignment? If we start this algorithm just from, say, take a random assignment, so just take from each bag random instances, how good are we going to do? Well, we can figure that out with this type of result. by plugging f equals 1 over, heuristically, we could plug f equals 1 over n, because in the large M limit, we're going to have a fraction 1 over n of matched assignments after the, if we just pick a random assignment, and then that gives us phi is scaling like ln n over n. And then this, if you compare this to what you expect the order of the deviations to be from the covariance estimation, which determines how different v hat is going to be from the scalar multiple of the, from the scaled concept vector, those are like d ln nm, and then you solve and you get how big does m need to be, which is going to be n squared. So the way to think about this MC is you want more than MC bags for this EM algorithm to converge just basically immediately in one step, okay? Now, this is generally in applications, n is big. M and n are like the same size, actually. So this is not that helpful in practice for telling us about the convergence of the algorithm in real life. It's just giving us a sense of an example of how these kind of different scales enter into this algorithm and how the extremal statistics play out. But that's one result you can get out of this model. So what I'm really interested in, what I spent most of my time thinking about, are generalizations of this that are, as I'll say in a moment, motivated by kind of the more modern architecture. So the real things, people are using for like pathology slides and immune repertoire classification are not these simple concept point models. They're more complicated, and they're often based on not just an extremal principle, but some sort of softmax pooling. So what you would do is you'd score now the instances with some direction in feature space or set of directions in feature space, and then you'd pool them and you'd compute sort of a weighted sum of instances. Okay. There should be another sum out there. Yeah. And there's also noise, modeled noise in the labeling process, right? So what we really want to understand is what happens to the EM algorithm as we take both these things to be peaked together. The softmax and the labeling sort of both become delta functions. So that's one part of it. And then the other part is the idea that we, again, for these more modern architectures, we really want to understand when there's a difference between the way that the direction feature space that we're using to select the instances that label the bag, and then how we label them. So we might have, for example, the label is determined by taking the instance, which is maximal dot product with some Q, which we often call a query, and then dot producting it with another vector V to get the label. And so that kind of geometry of the two, how we're selecting versus how we're labeling, and the interplay between them is really important. And this, again, as I said, the motivation here is that these modern architectures are based on what are called attention layers. And so, it says AI over there. So I think these attention layers are sort of, I have to mention these attention layers because that's, it's a big part of these AI algorithms. So nod to AI. But anyway, these were introduced actually for like large language models, machine translation, and then later imported into this multiple instance learning type of problems. How am I doing your time? Okay. Yeah. So again, one more thing I want to say about this is typically these attention architectures are trained with gradient descent. So people kind of moved from these like simple concept point models, EM algorithm, and then they went to attention models and sort of threw away the EM algorithm and just said, let's do gradient descent, because it's not so clear how to apply that to these or whether it works as well for these more complicated architectures. And so this is really what I want to think about. Here's kind of, again, more explicitly just the model we can consider, where we're now saying that I'm going to compute basically, I'm going to define a probabilistic model such that when I take its limit, I get that model I put up in the second point over here. So I'm going to now think about, to connect the attention view in the latent variable view, I'm going to think about sampling the assignment, okay, from some distribution, which comes from this softmax function, and then adding the noise to the label, okay? And I'm going to call, again, I use the term instead of calling it a concept point, when we talk about attention, it's called a query, but it's the same idea. It's like the direction of feature space that you're in feature space you're using to select your assigned instance. And then from this, you can get the posterior probability very easily of the assignment given the labels and the predictors, and it now includes both apart from sort of the residual and apart from the extremal selection rule. And if we think about the limit of this model as sigma epsilon, that's the label noise, goes to 0, and lambda goes to infinity, that's basically this extremal limit where we're just selecting the extremal assignment and we're assigning it a label. And so we can study that limit by defining an interpolating parameter kappa, which weights, it's basically measuring the relative rates at which these two things approach delta functions. The selection mechanism and the labeling mechanism approach delta functions. And then tau is like the overall scale, which I want to take to infinity, and I get the labeling scheme that I put up before. And this, when you take the limit of the EM algorithm as tau goes to infinity, what this gives you is a parametric family of iterations on assignment space parameterized by kappa, which will has the same structure as before, except now we have two things we're estimating, two vectors we're estimating, not just the concept point, but we estimate this value vector, the query vector that go with an assignment, and then we put that into this assignment function, which again now is more general than what I was using before, in that it interpolates between just the pure selection and using the information about the labeling. Okay, and its interesting thing is if you think about the data generating process being that hard limit I showed before, this kappa is not defined, right? Kappa is now an algorithmic parameter here. And what's also interesting to me is that this algorithm I showed before, which I don't think I mentioned, but it's called the EMDD algorithm for reasons that aren't so important. The one that the EM algorithm I showed before, that's actually not a special case of this. Okay, so that's another interesting thing here, is that the algorithm people have been using as the limit of the EM is not actually the limit of the EM. And the reason they do that, I now understand, is because when you do their version of the algorithm, as I explained, if you get a scalar multiple of the concept vector, it doesn't matter as long as it's pointed in the right direction. Here, it starts to matter when you're integrating the two pieces of information, when you're using the residual. I believe I'm running out of time. 2 minutes. Okay. So yeah, I have some simulations of this, these two algorithms. So I won't have time to say much about this, except that we do see that scale that I described before, the scale M that tells us how many bags we want for this algorithm to converge fast, appears as a transition here. These are just showing, like, if I run it for some fixed number of iterations, what's the final match fraction? So it's 0 is good. 0 means we got them all. And there's a transition here. If I try to, and this is the case where the query and the value are misaligned. So the older EM algorithm shouldn't work, and it doesn't work. I'm just showing that to illustrate it. I'll skip this. This is just more plots of the algorithm. I say I don't know problem. If you have Gaussian instances, okay, like I described, the setup I described, randomly sample the instances from Gaussian distribution, generate the labels by that model I just described. I don't know what the optimal way to adjust kappa is to solve that problem when they're misaligned. So that's kind of an open problem. The result I mentioned, you can generalize. So you can generalize these asymptotics of the value vector. There's some numerics there. There's some results I have about approximating the query vector, which doesn't have an analytical solution. And I'll skip this slide and just say that, okay, I think this MIL, it's a very cool problem. It appears throughout biology. I'm still kind of exploring. I'm getting into actually these genotype to phenotype mapping problems and how to recast them as multiple instance learning problems. I think there's a lot of, if you look in the literature, I'm not criticizing the literature, but a lot of things are ad hoc and done by computer scientists. And I think applied math has a lot to bring to this area. And I think there's a lot to explore, sort of just like thinking about random data. It's kind of a disordered systems view. And on a pedagogical level, again, it says AI over there. And, I think if you're interested, if you're sort of like, you're kind of curious about AI, these large language models, transformers, I find this to be a useful stepping stone to kind of learning about those ideas. And I'll end there. This is actually, I didn't say what this is, but these are softmax weights when you train that model using gradient descent. I have some other results about that and some interesting things that happen there. And so thank you to the organizers. Thank you to the NSF. And thank you. I have two students. One of them, Kalen, is working on this. He just got started on this project, and talking to him has been helpful for me about this. Cool.